Thank you so much. Okay, thanks for coming to our talk. My name is Guillermo del Castillo, Machine Learning Engineering Manager at Autodesk Research. And with me is Kamal, Rahimi, Malekshan, Principal Machine Learning Engineer. So today we'll take you behind the scenes on how we built at Autodesk RayLab. This is our internal platform for scalable deep learning workloads. Like many organizations, our teams were hitting the wall with large-scale model training, data pipelines, compute bottlenecks, and infrastructure complexity were holding back iteration speed. So our goal was to design a system that abstracts away infrastructure but still provides fine-grained control to power users. Built over Ray over Kubernetes. Basically, this talk is a story about scaling deep learning responsibly, improving efficiency, fairness, usability, while keeping research agility. So here's our roadmap for today. We'll begin by looking at the challenges that we faced scaling deep learning. From massive 3D image datasets to GPU allocation inefficiencies. Then we'll talk about RayLab's design, how we build Ray over Kubernetes to manage hundreds of experiments, datasets in petabyte scale, and distributed training and serving pipelines with minimal friction. We'll also touch on architecture, resource allocation, observability, and close with lessons learned and ongoing work with multi-tenant fairness and auto-scaling. Ultimately, this presentation is about how Autodesk went from isolated GPU jobs to unified production-grade research platform that scales across teams and regions. Yeah, next.
So the deep learning workflow often starts with identifying and ingesting data set. For example, for one of the projects that we have done in Autodesk, we ingested about 300 terabytes of data. During the data processing, often the data is deduplicated and converted to a format which can be consumed by the machine learning models. For this example project, for example, we generated about 100 terabytes of data and formats such as BREP, image, text, and other formats. During model training, several experimentations are done using different network architecture and hyperparameters, and the performance of the models are evaluated. Once the model performance are satisfactory, the model needs to be served behind an API to be used for the application. For this example, we ran more than 300 experimentation, and at the end we had more than 10 models in production. So large-scale deep learning is challenging. One of the main reasons is we are dealing with the massive data volume, and these data often are unstructured and are in formats such as 3D object, text, or images. There is also need for high computation, and we often need to use parallel processing across multiple instances. And we also often need to use GPUs or instances with special hardware for this kind of processing. So orchestrating this kind of job is often very complicated and needs some infrastructure expertise. So initially, we started with some of the existing solutions before adopting Ray, and we were facing several challenges. One of the first challenges was because of the long job startup time and deployment cycle, it was very difficult to iterate over the experimentations. Debugging experiment also was difficult because of the lack of central visibility. And also we were seeing long idle time for expensive GPU resources, which was inefficient use of the resources that we had. And finally, these existing solutions, they had limited flexibility and they were hard to customize for advanced distributed techniques. So Ray is a general purpose distributed framework which is built for Python, and it provides end-to-end machine learning support from processing to training and inference in a single stack. Using Ray is also easy to iterate fast, and debugging is much simpler because of the interactive development that Ray offers, as well as the real-time logs and live dashboards. Ray also provides fine-grained control over compute resources, scaling, and task scheduling. And it is cloud agnostic, so it can be deployed on any cloud infrastructure. And finally, it's open source and widely adopted. So Ray basically combines the power of the distributed compute with the agility that we needed for modern ML development at Autodesk. So to run jobs on Ray, we first need to create a Ray cluster. And a Ray cluster consists of a head node and a number of worker nodes that can be created on cloud virtual machines or a Kubernetes cluster. Once the cluster is created, so we need to use the Ray's Python SDK API to define jobs that needs to be run, that we need to run on the Ray cluster. So at the lowest level, Ray provides Ray Remote, which is for custom parallel tasks. And here you see an example code snippet for Ray Remote. As you can see, this is very similar to multi-processing code in Python. But the difference here is this code now can run on as many instances as we need. At the higher level, Ray also provides Ray data, which is for kind of a map-reduce kind of operation on the data sets. And Ray Train is provided by Ray for distributed training, such as using PyTorch and other framework. And Ray Serve is also for scalable model inference. So once we define the code using this API, so all we need to do is submit the job to the Ray cluster that we have for execution. So while Ray is very powerful, provisioning and managing clusters is complex for most of our users, which are ML researchers and scientists, as it requires infrastructure and cloud expertise. It was also very challenging for them to meet our internal security requirements that we had. On the other hand, for training model or large-scale data processing, we needed some other features such as experiment tracking and checkpointing, which are not part of Ray. So therefore, in Autodesk, we built RayLab on top of Ray, which makes using Ray easy, secure, and scalable, and adds the missing features that we need for our experimentation. So our RayLab basically have 4 main components. The first component is cluster management, which provides simplified interfaces to create and manage Ray clusters. The second component provides unified training and processing API, which is basically built on Ray's own API with some added functionality, for example, for checkpointing and experiment tracking. The third component is the smart job scheduling. This component provides us the ability to use priority-based job scheduling with different priority tiers, and also assign quotas to different teams and different type of resources. Resource efficiency and monitoring component is to provide real-time dashboard as well as active monitoring and Slack notification for all the experimentation that we are running. So this is a high-level overview of our multi-tenant architecture that we have. So as you can see here, we use Jupyter Hub to provision ML workspaces for the users. And we have different teams, so we map each team to a separate namespace. And we use role-based access control to granularly control the access of different teams to the data, as well as access of the users to different namespaces, essentially. So as you can see here, this is our RayLab SDK, which is built on top of Ray's own SDK and provides CLI, Python client, as well as a web UI to easily create and manage clusters. And you can also see here we have some other high-level Python APIs for training or data processing. So on the Kubernetes side, of course, we use KubeRay operator to create and manage Ray clusters. And we have some other components, such as Prometheus, Grafana, and role-based access control.
Yeah, thank you, Kamal. So now a little bit of code. So once the RayLab foundation was solid, our first priority was to simplify cluster management. So first thing, we created the CLI interface because we needed to be fast and developer-friendly interface. This is predefined with default values that users can quickly change and adapt their experiments. So if you can see here, with a single command, a user can create, destroy clusters, submit training jobs, or view logs, all without touching the Kubernetes YAML files or cloud consoles. Under the hood, what's happening is that the CLI will interface with the Ray operator and AKA's API. Will provision the head and worker nodes securely inside Autodesk environment. So what's the result on this? You'll be able to launch a full GPU cluster that used to take probably 30, 60 minutes. Now it takes under 2 minutes, albeit with compliance of and RBAC controls, as Kamal was playing. Next, we needed also a Python client. This is probably one of the favorites or popular interfaces for our researchers because allow them to programmatically spin up clusters directly from notebooks, pipelines, great for running experiments, hyperparameter sweeps, model refresh, jobs automatically. So the Python SDK's expose method to submit Ray jobs, monitor logs, and manage cluster lifecycle from within Python. So together, the CLI and Python client form the backbone of automation first philosophy for in RayLab. Last but not least, the UI web interface is designed to provide access and visibility. Not everyone wants to use terminal. So the UI allows scientists, researchers, engineers, even leadership to see cluster activity in real time. Metrics, see active jobs, GPU usage, logs, metrics. And admins can also inspect quotas and for fair usage and shut down idle clusters right away from the dashboard. So this visual turned RayLab from an infra tool to a collaboration platform and allow us supporting onboarding, transparency, accountability across our research org. Next, the fun part, distributed training. So once we had this framework ready, was in place, enabling distributed training at scale was the next step. But we didn't want to force researchers to rewrite huge chunks of code. So what we basically did is we took RayTrain and PyTorch Lightning, which it was one of our dependencies, into a single class that we call RayLab. Ray Lightning experiment. This unified interface allows us to scale standard Lightning jobs to multiple Ray clusters seamlessly, preserving the same code structure and training logic. So these also allow us to integrate or automate the checkpointing, saving, and logging. It goes directly to S3 buckets and reports metrics to Comet or TensorBoard. This setup enforces reproducibility, traceability, and it's being a key across multiple orgs for research collaboration. Multiple groups now can share training configuration through RayLab. So this is our simple distributed philosophy that distributed training should feel like local training, and that's what this interface achieved. And this is just an example that how in a single script we can define our own model, our custom model, our custom data set, and tweak the hyperparameters. You know, you can check the epochs you want to go, the training strategy, DDP, deep speed, FSDP, where you save, in what checkpoint, or sorry, in what bucket you want to save, number of workers. In our case, we use AWS, so we can specify what type of instance we want to start for a cluster. And it's basically simplify the training jobs and cluster management. And last but not least, this is an example of how once the jobs are launched, the challenge was visibility and debugging. So with RayLab, we wanted to monitoring to be built in, not just a third-party tool or an afterthought. This platform automatically collects time logs, job states, GPU utilization, training metrics, and expose everything through the web dashboard and CLI. So that the users now can drill into each experiment to see resources usage per node, live logs, even Ray internal metrics like the object store memory and task queue length. This level of transparency allows engineers to detect issues early. From example, identify issues, data loader bottlenecks, or uneven GPU utilization distributed across workers. Essentially, we turn RayLab from a black boxing into a full observable distributed system empowering our teams.
So as we started to train larger models and we started to scale up our cluster to use many more nodes, soon we realized the communication bandwidth between nodes becomes a bottleneck. So as you can see here in this example, beyond some scale, adding more nodes not only does not improve the performance, but actually it slows it down. So fortunately, AWS has an option to use fiber adapters between the instances, and this feature increases the default about 10 gigabit per second communication speed to up to 3 terabit per second. This feature in AWS is called EFA. But to use this, so some configuration is needed to be done on the infrastructure side. Also, we need to find out a combination of different drivers, basically, that work together, which is very challenging for average user. So using RayLab, we simplified all these. So our scientists, all they need to do is just use this enable EFA flag, and then they have access to high communication bandwidth between nodes, and then they are able to scale up their training or processing to much larger scale. Serving models using RayLab also is simplified. So here, these are standard RayServe Python code and a configuration. So using one single command, so we are able to create an endpoint for the models that we have been training. Another important consideration for us has been efficient resource utilization. So we have a number of expensive reserve GPU instances, and we have several teams that they need to use this GPU, reserve GPU instances for their experimentation. So originally we started with some unrestricted sharing strategy, but soon we realized that one team or even just few people may use all the resources while other teams are waiting for resources. So basically, this was causing inefficient use of our compute resources. To solve this problem, we started to assign a quota to different teams. Basically, a fraction of the GPUs that we had were assigned to different teams, and we enforced this using Kubernetes quota functionality. So using this, we were able to provide fairness between among different teams. But the problem was this was causing underutilization. So as you can see here, one team is assigned a number of GPUs, and they are not using it, and it stays idle. But on the other side, some other team may have jobs which are queued up. So to solve this problem, we introduced priority-based job scheduling. Basically, we allowed different teams to, in addition to normal jobs within their quota, to schedule additional jobs with lower priority, which we call it background. So the background job fill unused capacity by other teams. However, if the team which assigned the quota needs them, the background jobs which have lower priority will be immediately preempted. And also we have built some infrastructure such that the background job, when they get preempted, next time can automatically resume from the last checkpoint without need for any manual intervention. So using these two strategies, assigning team quotas and also priority-based job scheduling with background jobs, we have been able to increase our utilization and at the same time keeping fairness between different research teams. So here is our RayLab UI to manage resources, quotas basically. And so using this UI, so the admins are able to change quota for different type of resources such as CPU or different type of GPU, and for different teams simply by just a single click here. And in addition to team quotas, we also provide a functionality for admins to see all the current jobs in our cluster and their utilization. And admins are able to put limits on different jobs and basically move resources between different jobs if needed. We also have dashboards to monitor the current assigned quotas for different type of resources to teams and the current utilization, as well as the status of different priority queue and the jobs which may be waiting. We have also dashboards to monitor the utilization efficiency, which is in terms of the percentage of GRAM utilization or GPU compute utilization, and many other metrics per teams and or in general in the whole cluster that we have. And in addition to monitoring dashboard, we also have active monitoring. So our active monitoring monitors all the current jobs in our cluster. And if it notices there is a job which is not efficiently utilizing resources, it sends a direct message to the person who created the job with some tips on how they can improve the utilization efficiency on their job. But if the job is very inefficient and it's very expensive, so our monitoring app will automatically takes away the resources from the inefficient job so it can be used for other jobs in the queue until the problem is resolved. So in summary, we talked about how Ray and KubeRay enabled us the control, flexibility, and scale that we needed for large-scale deep learning. So we have built RayLab, which abstracts away the infrastructure while also keeping the functionality that power users would need to customize their experimentation. And we also talked about how our priority-based scheduling and quotas enabled us to more efficiently utilize our reserved GPU resources. And we also showed how the RayLab CLI, UI, and SDK makes it easy to onboard new users and also experiment on Ray clusters.
Thank you. So to conclude, RayLab has become Autodesk's backbone for scalable AI research, supporting multiple projects in generative AI, CAD, and 3D. So if you're tackling similar challenges, multi-tenant Ray, on Kubernetes, fair scheduling, or distributed training, come talk to us after the session. A huge, big thank to Autodesk Research, Engineering, RayLab, platform teams, people listed here. We couldn't have made it possible without you, so we're very proud of you. Yes, we're continuing to evolve Ray and RayLab, and so we're hiring, so please, you can find us in Autodesk career site or reach us directly through LinkedIn. Thanks so much. We'll take a few questions.
This is super cool, thank you. Maybe 1 or 2 questions.
Hi, thank you so much for the session. I was curious about the observability part that you showed about the reactors usage and kind of the real-time metrics usage. I'm assuming that those metrics are generated by Ray and you scope through Prometheus, etc. The UI there was your own RayLab UI, or were you using any open source UI to actually show all of that?
So you are talking about this?
The actor metrics in some previous slides, right, where you showed, hey, this is the utilization of the Ray cluster, and for example, how many actors were used, what was the Ray data, etc. I saw one of the slides back there, something. So again, I'm talking about more, yeah, this one. This one.
No,
yes.
This is basically a standard, sorry. This is basically a standard Ray dashboard. It's not ours, but we have set up, like, let's say Prometheus and other dashboards here, yeah. That's a great question. Actually, we are using auto-scale in Ray clusters, so often the head node is a very small node, which we keep it running and doesn't cost much, maybe $8 a day or something. And then our researchers or ML engineers submit jobs, and then clusters auto-scale and downscale when the job is done.
I guess follow-up question on that, are you persisting any of the dashboard data? Sorry, Spencer here. We're running Ray dashboards as well. We don't leave our head nodes up, so we lose the dashboard. Are you doing any persistent stuff with this? Have you figured that out, or are you just leaving the head nodes running and hoping they stay up?
So I think you are asking about persistence of the logs, probably. So in addition to Ray, we are also using Comet for experiment tracking, which we have access to all the logs, and also we logs a lot of basically information about the cluster to S3. That's another way that we can track the experiment. Yeah, there are some other ways, I think, to persist the logs, but so far we have been using just Ray cluster itself and Comet for experiment tracking.
Have another question there?
Manan here.
Yeah, sure.
I'm curious how your background jobs preemption works. Do you have a mechanism to have your research folks build some preemption hooks, or just curious how it's set up right now?
Yeah, that's a great question. So when we submit background job, we use Kubernetes different level of priority, and we configure that such that lower priority jobs are preempted when the higher priority jobs are scheduled. And we use some of the Ray functionality, and so when experiment fails, we keep trying until they get the resources. And when they get the resources, we know where's the last checkpoint in S3. We download that and then start resuming the experiment.
Yeah, thanks for the talk. Can you talk about the way in which the researchers are interacting with the cluster? I know you have the Python SDK and the CLI. Are they SSHing into any of the nodes? You also talked about Jupyter Hub. I know a lot of people now want to use the new IDEs like Windsurf and Cursor. So how are they actually interacting with the cluster? Or are they doing everything on their laptops and then they're just submitting Ray jobs and then looking at the logs?
Yeah, so most of our work is performed in a production environment, so which they need to be isolated. So we don't provide access in a laptop level, so everything is in cloud, and it's a Jupyter Hub workspace. And within that workspace, we provide access to a code server, which basically can use Copilot. Yeah, Cursor is still, they don't have a basically web-based IDE, so that's why we don't have that functionality. But to answer the question, yes, I think everything is in a Jupyter Hub environment, and it's a protected environment, but researchers have access to the RayLab UI and CLI, as well as the VS Code IDE to do all experimentation, basically.
Hey, thanks for the talk. So I understand Ray also does provide a lot of the observability as well as the checkpointing. So I am not sure I fully grasp why this RayLab was needed. Can you talk a bit more about the security concerns that like made this a requirement?
Yeah, so we are not creating something which Ray doesn't have it. We basically take full advantage of everything that Ray has it, but we build around it things that we need basically on top of it. So for example, if you want to create a Ray cluster on a Kubernetes cluster, you need to create a YAML file, and that YAML file should have all the information that you need, which is not easy for ML, I would say, researchers to understand what is that. But with RayLab, we basically abstract away all those low-level information, and we just provide them a simple, let's say, CLI, and underneath we auto-generate what Ray actually needs. So yeah, it's a one-line, basically one-line command. So that's the main reason for RayLab.
All right, let's thank you the speaker one more time.
Sure.
Thank you. And we can follow up offline, but we have to stop the recording now. Thanks.
We can continue.